Hello, this is Dr. Strickland. In this video, we will begin our investigation of kinetics, talking about free energy changes and free energy barriers. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So kinetics is concerned with how you get to equilibrium. And a lot of it is how fast you get to equilibrium, but that's not all of it. So how fast is tied up in rates, but we do talk about energy barriers and the mechanisms that are involved in transforming reactants into products. Now, the energy barrier of a reaction is also called the free energy barrier, and you can see it's got that delta G, but it's got this little superscripted sort of double plus sign thingy. So it's the amount of energy that must be present for the reactants to be converted into products. Because before you can convert almost every reactant, you have bonds to break, and it takes energy to break bonds. So you have to get that energy together, whether it's from the reaction being heated or the energy just in the environment. You have to be able to get that energy together. The other thing about this energy barrier is anything that will make the reactants less stable, having more energy, or making the transition state more stable, having less energy, will decrease the delta G and make the reaction go faster. So this free energy of activation, as you might recall, is the distance between, let's do this one as an example, is the distance between the reactants and what's called the transition state. And I'm going to do TS for transition state for now. We'll talk more about that down the road. And the products are over here. Yeah, and this is true of any reaction coordinate diagram. So the free energy of activation is the amount of energy that the reactants have to get together in order to get up this hill and turn into the transition state. All right, so the difference in energy between the reactants and the products is the free energy of the reaction, and that's what we were talking about when we were doing thermodynamics. All right, so we're going to talk some about thermodynamic stability and kinetic stability right now. Thermodynamic stability is done for products. So thermodynamic stability is revealed by the sign of the free energy change of the reaction. So, and we talk about whether a product is thermodynamically stable or thermodynamically unstable. If it's thermodynamically stable compared with the reactants, delta G will be negative. And when delta G is negative, then the products are more likely to form. Okay, so thermodynamically unstable is the opposite of that. So delta G would be positive, which reveals that it's more likely to just stay as reactants and not turn into products. So I put a key down here with R for reactants and P for products. TS will be thermodynamically stable and TU will be thermodynamically unstable. So we'll use these here in a minute. Let's look at these. Kinetic stability is done in terms of reactants. So kinetic stability is revealed by the magnitude of the free energy of activation. And a reactant is kinetically stable when this value is large, which reveals that it's converted into products slowly. So kinetically unstable would have a small value of this, which meant that the reactants were converted into products quickly. And I've got KS for kinetically stable and KU for kinetically unstable. But let's look at the thermodynamic stability or not of these products, and then we'll come back and do the kinetic. So you can see right here that with this reactant and product that we've got a negative delta G. And that means that this product is thermodynamically stable because it's got a negative delta G. All right, so do we have any others that are thermodynamically stable? We've got 4 here, A, B, C, and D. So this one has a negative delta G also. So this product is also thermodynamically stable. And you could say delta G is less than 0, or you could say it's negative. That would mean the same thing. Now in C and D, you can see that the delta G from reactants going to products is a positive value. And that means that the product is thermodynamically unstable. It's less likely to form. So the product is thermodynamically unstable because you've got a positive value. You could say, the products are less stable than the reactants. So that would mean they're more unstable. Same thing is true here. Positive delta G. All right, so with thermodynamic stability or not, you're dealing with a negative value versus a positive value. So with kinetic stability, we're talking about large versus small values for the distance in energy, the difference in energy between reactants and transition state. So when we do this, we'll try really hard to make it obvious whether we're talking about something small or large. So let's just put these little labels for reactant transition state products for all of them. Okay, so these two have free energy of activation values that are relatively small. So when it's relatively small, we're talking about kinetically unstable. So the reactant is kinetically unstable because we've got a small value of this energy hill. All right, so this one also. All right, a relatively small value of that energy barrier or energy hill. So it's more likely that no, I don't want to say it that way. The reactants will turn into products faster when you have a small value here. When you've got a larger value, like you do in B and D, then the reactants are kinetically stable. And that's because you have to get so much energy together that it's less likely that this would form. And if it does form, it's much slower. So the reactants are kinetically stable in both of these cases because the free energy of activation is large. All right, so let's just put those designations in these places. And you can see we've got all four possibilities here. This one, this one, this one, and this one. Okay, so make sure that you understand how that works. All right, so we just got it in words down here, just as an alternative. If your product is thermodynamically stable, it's more likely to form. But if it's thermodynamically unstable, it's less likely to form. So whether it's likely to form or not has to do with the thermodynamic stability of the product. But how fast it will go has to do with the kinetic stability of the reactant. So if you have a larger free energy of activation, it forms slowly. If you have a smaller free energy of activation, it forms quickly. And let's change forms. Let's change that to reacts. I think that's a better word here, because we're doing kinetic stability in terms of reactants and thermodynamic stability in terms of products. Okay. All right. So that's the basic story on thermodynamic and kinetic stability. If you have any questions, please send them to me.